All right, in the world of cryptography, there's always this one big idea, this sort of holy grail we're all chasing, a way to actually use data without ever having to expose it. Well, today we're going to talk about a technology that gets us incredibly close to that goal. It's called homomorphic encryption.
Just think about that for a second. Seriously, can you compute on data you literally cannot see? Imagine you have a locked box. You hand it to someone, and you ask them to do something to what's inside without ever opening the box. Then they hand it back, and you're the only one with the key to see the result. Sounds a bit like magic, right? But that's the core problem we're talking about.
And believe it or not, this is the revolutionary promise of homomorphic encryption. It actually lets us keep that box locked, protecting whatever sensitive info is inside while still letting a third party do valuable, important work on it.
Okay, so let's dive in. Let's get a really clear idea of what we're talking about here. How does this even work in principle?
So this is the fundamental idea. See, normally, if you want to compute on some data, you have to decrypt it first. And that moment of decryption, that's a moment of vulnerability. The real magic of homomorphic encryption, we'll call it HE, is that you can do the math, things like addition or multiplication, directly on the scrambled, completely unreadable encrypted data.
And this right here, this is the unbreakable rule that makes it all work. If you add two encrypted numbers together, the answer you get back once you decrypt it is the exact same answer you would have gotten if you had just added the original unencrypted numbers. The math just works straight through the encryption.
And this flow really shows you where the security boundary is, which is so critical. Your private data gets encrypted on your machine, right, before it ever leaves. Then it's sent off to some cloud server, which does all the heavy lifting, the actual computation. But, and this is the whole point, that server only ever sees gibberish. It only sees the encrypted data. Then, that encrypted result comes back to you, and only you, with your private key, can unlock the final answer. The raw sensitive data is never exposed out there in the wild.
Now, you might be thinking that homomorphic encryption is just one single thing, but it's really not. It's more of a spectrum of different technologies, and each one has its own capabilities and, just as importantly, its own practical trade-offs when it comes to performance and what you can do with it.
This table kind of lays out the landscape for us. On one end, you've got partially homomorphic encryption. It's super efficient, but only for one specific operation, like addition, over and over again. Then, in the middle, there's somewhat homomorphic encryption, which can handle a limited mix of operations. But the real goal, the thing everyone is shooting for, is all the way at the other end.
And yeah, this is the ultimate prize, Fully Homomorphic Encryption, or FHE. With FHE, you can do pretty much any computation you can think of, no matter how complex, all on encrypted data. Now, as you can probably guess, that incredible power comes at a cost, usually in performance. And that's been the big challenge for us cryptographers for a long time.
You know, for decades, FHE was just a dream. It was a purely theoretical idea in cryptography. So what was that moment? What changed that turned it from an academic concept into something we could actually build?
This timeline really puts that progress into perspective. For the longest time, we knew what we wanted, but we had no idea how to actually build it. And then, one single breakthrough just completely shifted the entire field. And we've been building on that foundation ever since.
That year was 2009. A cryptographer named Craig Gentry, for his PhD thesis of all things, built the very first plausible fully homomorphic encryption scheme. He figured out how to solve this massive problem of noise that builds up during computations using a brilliant process he called bootstrapping. That one idea basically opened the floodgates for everything we see today. So, okay, we've got the theory, the different types, and the history. But what does this actually mean for the real world? Why is being able to compute on locked data such a massive game changer? What it means is that we can finally outsource heavy computation without having to outsource our trust. Think about it. You could train a machine learning model on super sensitive patient data from a hospital, or run financial analytics on confidential company records. Before FHE, you either had to water down the data to anonymize it, or you just had to completely trust your cloud provider not to peek. FHE lets us do all that work securely without ever exposing the raw data to anyone. So let's just walk through that flow one last time, because it is so fundamental. Your data starts on your device, and it gets locked. It travels to the cloud for some serious number crunching, and it stays locked. And the result you get back is still locked. You and only you have the key. That's the promise of secure computation finally made real.
So, we've gone from something that was thought to be impossible to something that's actually practical.
The journey from here isn't about if we can do it, it's about engineering. It's about making these systems faster, more efficient, and easier to use for everyday tasks. The question is no longer can we compute unlocked data? The real question is, as this power becomes more and more accessible, how are we going to use it to build a more private and secure digital world?